Well, hello and welcome to the 17th lecture of this short course called Behavioral Theory of Systems with a view towards data driven control. So, in the last lecture we were in the last lecture we established this idea of fundamental principle, right, and then in the last lecture we used fundamental principle to carry out this extremely important task that we are often required to do, which is the so called elimination of variables, right. We looked at this particular example of state space representation, and we argued that okay, state is like a latent variable. We are interested in the behavior of the input and the output. So, given a state space representation, input state output representation, how to get rid of the state variables to get a representation involving only the inputs and the outputs. Yeah, that was one particular example of an elimination process. Now, algorithmically what the process says as per fundamental principle is the following, that if you have a system of differential equations which looks like this, yeah, where these are polynomial matrices, differential operators, W is the manifest variable, L is the latent variable. You want to get rid of the latent variable L. What you do is look at this R to xi matrix and then from here obtain its maximal left annihilator matrix, the maximal left annihilator matrix. Yeah, this is such that when you do this multiplication of two polynomial matrices you get 0, and this M also has this added property that every row vector of proper size which satisfies this condition must imply that this row vector is in the row span of this matrix M. Then we call this M the maximal left annihilator. I should say a maximal left annihilator because there could be multiple matrices, but in any case the module is the same. The column the row span module this must be the same. In any case we call this the MLA matrix, yeah, the maximal left annihilator. So, given this equation, look at this R2, the matrix that operates on the latent variable that you want to eliminate, and look at its maximal left annihilator matrix M. Then a kernel representation for the manifest variable is given by so B, which in fact is equal to, by definition, projection of the full behavior. What is the full behavior? Full behavior is the behavior of W and L that satisfies the equation R1 xi W plus R2 xi L equals 0, right. So, this is the projection, and this projection in fact is given by kernel of the maximal left annihilator of R2 acting on R1. Yeah, that is the elimination theorem. Okay. And we looked at one particular example to carry out this process and show how this process actually works, right. And we in fact, if I am not mistaken, we looked at this transfer function, yeah, which is given by s plus 1 divided by s plus 2 into s plus 3, a very simple one, right, and this is just s plus 1 divided by s squared plus 5s plus 6, isn't it? And we obtained a state space representation for this one, namely x dot equals 0 1 minus 6 minus 5 x plus 0 1 u. Just by inspection you can write it, and y equals 1 1 x, right. And from here we eliminated x to obtain kernel representation involving y and u, which in fact looked like xi squared plus 5 xi plus 6 minus xi plus 1. This minus can be here or here, does not really matter. because it is a kernel representation acting on YU equal to 0. That was the manifest behavior, and we obtained this using the elimination theory, using fundamental principle. Now, if you look at this YU, this relation, this in fact matches this tallies with the fact that the transfer function looks like this. Okay. So, I hope you are convinced that this elimination principle, the elimination theory that we have developed using the fundamental principle actually does the job that it was supposed to do. But now there is a subtle thing that I would like to discuss here, which will lead us nicely to our next topic. So, what if I do a little bit of tweaking here and change this guy to 1, right? All of you, I am sure, already know that this is problematic, because this causes this pole 0 cancellation, and then effectively the transfer function becomes 1 by s plus 3, right. That is the transfer function. So, if we carry out the similar tweak in the state space representation also, and try to do this elimination of x, what do we really get? Let us try and do this exercise ourselves by hand, so that we get the idea that what is really happening here and what is expected in such a situation. So, let me write down the transfer function here without doing the pole 0 cancellation. Gs is equal to s plus 1, and now because I have s plus 1 multiplying s plus 3, I must have s plus 1 divided by, if I expand this out, s squared plus 4s plus 3, right. This is how it is going to look like. Now, suppose I obtain its state space representation like the way I did before. What will it look like? It is going to look like x1 dot x2 dot is equal to 0 1 minus 3 and a minus 4, and then x1 and x2 plus 0 1 u, okay, and y of course is equal to 1 1 x1 x2. You can easily check that this guy is controllable. Yeah, this is your A matrix, this is your B matrix, this is your C matrix. A B pair of course is controllable. Those of you who have done multivariable control, state space theory, know that this is indeed controllable. You can go ahead and check that this is controllable. Is this observable also? Well, I tell you that it is not observable, because if you look at the C and CA, this matrix, the observability matrix, what do you get? C of course is 1 1, but CA is 1 1 multiplying this matrix, right, the A matrix, and 1 1 multiplying this matrix is nothing but the row obtained by adding these two rows, right. And what is that? That is minus 3 and minus 3. You see, this row and this row are dependent on each other. In fact, the second row is just minus 3 times the first row, okay, which means the rank of this matrix is in fact equal to 1. So, the rank is not full, so therefore, it is not observable. So, what if we eliminate x now? What is expected in this situation? Let us try and do this exercise of eliminating the variables. Yeah. So, I write y u x1 x2 and write down the equations here. Okay. First one is 0 0 and x1 dot is equal to x2, right. That is the equation. The first one says that x1 dot is equal to x2. So, x1 dot is equal to x2, right. Second one is u with a minus sign, and x2 dot is equal to minus 3x1 minus 4x2 minus c. So, x2 dot plus 4 3, yeah. So, x2 dot plus 3x1 plus 4x2 is equal to u. So, this is the equation, yeah. Now, finally, we have y is equal to sum of x1 and x2, yeah. So, this is my equation So y u x1 x2 is equal to 0. So this is a kernel representation for the full behavior. I want to obtain the manifest behavior from here. Elimination process tells me that I need to find out maximal left annihilator of this matrix xi 3 1 minus 1 xi plus 4 and 1. Okay. Just like before, we do this trick of column operations and make this guy 0. This guy of course is going to be then xi squared plus 4 xi plus 3. This will be xi plus 1 and this is minus 1 xi plus 4 and 1. So it looks very much similar to what we had done before. But now when I try to find out the maximal left annihilator, once again the same logic will apply. This is like a 3 cross 2 matrix. So only one row is enough. One row of size 3 is enough to get me the maximal left annihilator, provided that there are no common factors between those 3 entries in that row vector. Yeah. So to get that, first I look at this equation. So once again I need alpha, beta and gamma, yeah, which when multiplies to this guy must produce 0 for both these columns. Yeah, that's the deal. Okay. How to get that? So I can use the first column to get beta and gamma, right? Now notice xi plus 1 actually is a common factor between this and this. So like before, I could have taken beta to be equal to xi plus 1 with a minus sign and gamma equal to xi squared plus 4 xi plus 3, but that actually is redundant, you know, because I could also have achieved the same thing by taking instead of this this I don't take, but instead I take minus 1 here, and for gamma I take xi plus 3, you see, because in that case, you know. So let us just check, yeah, with what happens with the second choice. I want beta times xi squared plus 4 xi plus 3 plus gamma times xi plus 1 to be equal to 0, isn't it? That's what I want. Yeah. Now let me show you. You see, beta, this is actually xi plus 1 times xi plus 3 plus gamma xi plus 1. Okay. So in order to have this, I could just cancel this out, and yeah, I could just take beta to be equal to minus 1 and gamma to be equal to xi plus 3. That's it. You see, that's the choice we made. That's the choice we made. So this also is good enough. Now based on this choice of beta and gamma, I will now get alpha, because alpha must satisfy from the second column, alpha must satisfy that it must be beta times xi plus 4, it must be beta times xi plus 4 plus gamma times 1 which then is equal to minus xi minus 4 plus xi plus 3, which then says this just cancels out and I am left with minus 1. Okay, I think I have not made a mistake anywhere. Let us just check. So my proposed maximal left annihilator is minus 1 and xi plus 3. Let us check whether this actually satisfies the equation, the two equations or not. Minus 1 xi plus 3. This should multiply to R2 and produce 0. What was R2? Xi 3 1. Okay, xi 3 1 and minus 1 xi plus 4 1, minus 1 xi plus 4 and 1. Let us check. So first product is going to be minus xi minus 3 plus xi plus 3. This times this. This indeed is 0. So first one checks out. The second one is plus 1 minus xi minus 4 plus xi plus 3. Okay, xi will go away. 1 plus 3 4 minus 4, this also is 0. So, the second equation also checks out. So, this indeed is equal to 0 and this has no common factors. Yeah, so therefore, every other thing, every other row vector of size 3 that kills this matrix must be a multiple of this guy. So, this is my maximal left annihilator. Lovely. You might argue that okay, why this and why not the first choice that I made about what was wrong with it. You see, if I had done this, I would have got a common factor between the three. I can just show you that. Yeah. So, let us say here we made the other choice. Yeah. Suppose I take beta to be indeed equal to xi plus 1 minus xi plus 1 and gamma to be equal to xi squared plus 4 xi plus 3, which is in fact xi plus 1 into xi plus 3. Okay. In that case, alpha once again will come out to be minus xi plus 1 times xi plus 4 plus xi plus 1 times xi plus 3. So, in this case also I could just take xi plus 1 out common and I will be left with minus xi plus 4 plus xi plus 3, which once again will come out to be xi and minus xi will cancel out, minus 4 will be minus xi plus 1. You see. So, in that case, instead of this I will get minus xi plus 1, yeah, minus xi plus 1, and here I will have xi squared plus 4 xi plus 3. Yeah. This cannot be a maximal left annihilator, because you see the property of the maximal left, property of any row vector that kills this R2 xi, yeah, equal to 0. Okay. You see, we have already checked that this is true. So, R xi can be this vector, but my proposed maximal left annihilator was xi plus 1 out common minus 1 xi plus 3. Can this R be in the module generated by this guy? Of course not, because this is, how do you get R from this? How do you get R from this? You have to divide by xi plus 1, right? To get this R, you have to divide by this guy. Division is not allowed in polynomial ring. So, it is not there. So, this in fact is a much smaller module than the module generated by this guy, and remember, maximal left annihilator should give you the biggest possible module. Its row span must be that whole module that that gives us all those R's for which this is equal to 0, and this equation is satisfied. That is why the maximal left annihilator. So, therefore, this choice that we made was the correct choice. This was the correct choice and this was a wrong choice. But now that leads to a sort of a confusion. What confusion? Well, now remember my maximal left annihilator is minus 1 and xi plus 3. Okay. So, how do you get the manifest behavior? This should multiply R1, which happens to be this acting on yu must produce 0. What is that now? Well, that comes out to be equal to minus xi plus 3, yeah, and plus 1, you see, acting on yu equal to 0. So, the pole 0 cancellation, the effect of the pole 0 cancellation is showing here. Although I wanted to get rid of that, I did not consider it, but notwithstanding that, I ultimately get a behavior which is just first order, right. So, what is the reason for this to happen? Although I had a state space representation which was second order, but ultimately when I eliminated the state variable, I got a first order system. The reason is that by the very construction I have made sure that it is controllable and not observable. Now, remember your state space, go back to your undergrad control courses. If you have a state space representation, yeah, this is your state dynamics, which receives the input and produces x, yeah, the state variable that passes through this C, assuming that there is no direct feed through term, that gives you Y. Now, if this is kind of broken and you have lost observability, then some of the dynamics of the state variable will not show up as a dynamics on the in the Y variable, right. So, although my second order system was although my state space system was second order, because of loss of observability, Y had only first order dynamics. So, whether it was controllable or not, that does not really matter, because it was controllable if the input was affecting both the states, right. But input cannot affect the Y as well as its derivative, yeah, both these state variables, because Y has only first order dynamics. That is why when we get the manifest behavior, we have only a first order dynamics involving Y. Yeah. So, then is it okay to do the pole 0 cancellation or not? Well, so for us, although we started with this system, actually our goal was, this was the way of constructing the problem. Our problem really starts from here. Our problem starts from here. Somebody gives us a latent variable representation. In this case, it is a particular kind of latent variable representation, namely state space representation. But then from there, if we start from if this is our starting point, then after elimination, if I get first order, then I should not get flustered about that, because it's very well possible that there was some problem with observability, and both the dynamics, both the state variables were not affecting the output. So, no wonder that the output was coming out to satisfy a first order equation. Now, contrast this situation with another state space representation of the same thing, of the same system, but now I assume that it is not controllable, but rather observable. How to make sure that this is the case? Well, I can just factorize these two. So, if it is a state space system with one, look at this guy, look at the state space representation, the A matrix, it has one eigenvalue at -1, another eigenvalue at -3. So, what if I obtain a diagonal representation? Yeah, just look at this now. Suppose this is my starting point, x1 dot, x2 dot is equal to -1 0 0 -3 x1 x2 plus 0 1 now u, and y is equal to, like before, 1 1 x1 x2. Yeah, you see in this case the transfer function once again remains the same, although that should not be our concern. We are not bothered about the transfer function at all, but this is another state space representation. Yeah, this is once again our starting point. The transfer function wise, the two are the same. Yeah, the first example and the second example. I want to eliminate the state variable x here. Now, let us see what happens. You can easily check that this guy is not controllable. This AB pair is uncontrollable. Yeah, but the CA pair is actually observable. You can check that this CA pair is observable. In this situation, what should we expect? Even if it is uncontrollable, it is a second order dynamics, and y, x is observable from y, which means y must also satisfy a second order equation, because both the state variables influence the y, yeah, independently. Therefore, y must also satisfy, because x has two components. So, it is a second order system, y is observable. So, it is expected that y should satisfy a second order differential equation. But that second order differential equation must be such that the input will not be able to influence its y and its derivatives independently, right, because it is not controllable. So, let us see what happens when we eliminate x from here in this situation. Okay. So, once again I am going to write down my equation. Yeah. So, y u x1 x2, the kernel representation for the manifest for the full behavior, that is 0 0 xi plus 1 and 0, because it is a decoupled system, remember. 0 minus 1 0 xi plus 3, okay. And here once again I have minus 1 0 1 1, that is it. So, in order to eliminate x, I need to find out MLA of the following matrix. I need to find out MLA of xi plus 1 0 0 xi plus 3 and 1 and 1. I need to find out maximal left annihilator of this guy. How do I get maximal left annihilator of this guy? Well, you can go ahead and check that an MLA for this can be found out by doing okay, I will put 1 here and xi squared plus 3 xi plus 4 xi plus 3 plus 4 xi plus 3, okay, with a minus sign and 1. You can go ahead and check that this is maximal left annihilator. It satisfies both the equations. Oh, sorry, my bad. I made a mistake. I made a silly mistake. This is going to be xi plus 3 and this is going to be xi plus 1, right. Yeah, now it is fine. See, you can easily check the first product, this with this will be xi plus 3 times xi plus 1, which is this polynomial. So, with a minus sign it will go to 0, and for the second column this plus this, that is once again this polynomial, with a minus sign it will go to 0. Yeah. So, this is my maximal left annihilator, and there are no common factors, of course. This do not have common factors, so obviously they cannot have common factors here. So, we do not have common factors, this is maximal left annihilator. What happens to the manifest behavior then? So, all I have to do is I have to now find out this, the product of this guy with R1, which is 0 0 0 minus 1 0 minus 1 0 0 0 minus 1 minus 1 0. What is this? This is going to be xi squared plus 4 xi plus 3 and minus xi plus 1. You see, isn't this surprising? This is the kernel representation for the manifest behavior. The manifest behavior now has this two polynomials, the common factor is there intact. Yeah, one might ask the question, is this behavior the same as the behavior that we had obtained before? What is your answer? This is my behavior 1, which is the manifest behavior from the earlier state space representation, and this is my behavior 2, when the manifest behavior obtained from the other state space representation. Transfer function wise both are the same. Are these two behaviors equal? What do you think? Can they be equal? They are not. Go back and check that for C infinity behaviors to be the same, their row modules need to be the same. But are the two row modules the same here? They are not. Look at the two row modules. One is just xi plus 3 minus 1, that is one row module, and the other row module is xi plus 1 times xi plus 3 minus xi plus 1. Transfer function wise, if you get rid of common factors, then they are the same, but here you do not get rid of common factors. Here this module is bigger than this module, this is a smaller module. Because this is a smaller module, this behavior, which we call behavior 2, this is a bigger behavior than the original behavior. Yeah, because this row module R1 and this row module R2 has the property that R1 is bigger than R2, strictly bigger than R2. Therefore, the behavior satisfies the opposite containment. Isn't it surprising? The reason is that, as we will see in the next lecture, this behavior B2 is an uncontrollable behavior. Now, that is different from a state space representation being uncontrollable. It is an uncontrollable behavior. Which means it is the property of the behavior itself that it is uncontrollable. It is not property of the equations. Yeah, of course, equations will be there to tell you that to tell us whether a behavior is uncontrollable or not. The tests will involve the equations, but the property of being uncontrollable is a property of the system, of the behavior. Yeah, and because of this uncontrollability, the transfer function comes out to be first order, but the corresponding behavior is still second order. This and many more is what we are going to see in the next lecture. Till then, take care of yourselves and bye from my side.